Let's talk about AES67 and ST2110-30 over the WAN. But first, what is a WAN or wide area network? A wide area network is the interconnections of local area networks. Typically, this interconnection is using gateways to go from LAN to WAN, and then either a leased line, for instance a dark fiber, or the internet or a VPN. And typically, LAN connection is done between local area network or data center, where you can have virtual appliances, or multiple local area networks, or even sometimes endpoints. But why would I need AES67 on a WAN? Of course, because of COVID, and because of the rising need of remote production, and especially production from home or between different sites. And of course, most of those productions can be done offline by exchanging files, but some of them must be done live. And then this is where AES67 comes into play and can be really useful. So this work of exchanging AES67 on WAN has started after the first outbreak of COVID-19 at the Audio Engineering Society in the Standard Committee Group 0212M, and aims at answering the following questions. What can I do with my AES67 device over WAN? What can I add to my network to strengthen the WAN connection? And what should manufacturers add to the equipment to make them WAN ready? Of course, this is work in progress, and this presentation is only aimed at presenting some of the preliminary results from this working group. So, Internet is IP, and audio over IP is IP too. Isn't AES67 WAN ready by design? Well, not really. AES67 and ST2110-30 were built using LAN constraints in mind. This means small distances, private and controlled network, and few restrictions. Small distances will allow a high quality of clock recovery with PTP. A private and controlled network will allow us to transmit multicast, and few restrictions will allow us to not care about the bandwidth. On the contrary, wide area network use long distances, leased or public network, where you cannot do whatever you want on it, and especially not necessarily be able to transmit multicast. And those networks have other limitations, notably in terms of bandwidth. So typically in the audio world, what we use in those cases is ACIP, or Audio Contribution over IP, which is described in EBU text 3326. But of course, if you want some specific features, you might be after AES67. And those features are precise timing of the streams. For instance, when doing lip sync, you want precise synchronizations of your audio and video streams. PCM quality, which can be really useful for later processing, and low latency for real-time operations, so from 5 to 250 milliseconds. If you don't need all of the above, well, there might be other protocols that suit your need better, but if you need all of the above, then you need AES67 on WAN. So let's see the different programs that are associated with using AES67 on WAN. First, you have a delay and jitter program, because the light is only traveling as fast as the speed of light. When you increase the distance, data travel time is becoming significant. So for instance, here I'm in Grenoble, France, and Merging Technologies office is in Lausanne, Switzerland. This means 200 kilometers. But it's not as easy as that, because the connection, the internet connection between those two goes by many different points. And when doing a ping test, a measure of the round trip time between my IP address and the IP address at merging, it gives me that it needs 16 milliseconds at least, and at most 42 milliseconds to do the round trip. This in turn means that the audio coming from one point to the other will travel at least in 8 milliseconds, and at worst in 21 milliseconds, meaning that I will roughly need 30 milliseconds of buffer for the audio to be successfully received. And this is usual because over the internet you travel, the data is crossing many IT equipments and it has to cope with other traffic and the suffer speeds, conversion, etc. So the outcome is that on the LAN, whereas the delay and jitter can be really small and you can have buffer as small as 2 milliseconds, on the WAN you will have much greater buffers, both caused by the geographic delay and by the packet delay variation. And so much higher than you may need buffers that go beyond the AES67 recommendation. Luckily for us, most of the AES67 devices and ST2110 devices allow us to set for higher buffers. Then there's the timing and sync problem. AES67 and ST2110 are using PTP and the PTP timescale, which is the International Atomic Time, or Temps Atomique International in French, and starting at January 1st, 1970. This means that this time base has to be shared precisely between all the sites that are exchanging AES67 streams. And to do that, you have many different possibilities. The first one is to use PTP synced with Global Navigation Satellite System. So on each site, you will have a different master, but all those masters will be synced using GPS, basically. This is expensive, but really simple in terms of operation, although it can be impractical in the difficulties of properly placing the GPS antenna. You could also transmit PTP over the WAN, which in turn can be imprecise for the problems that we just talked before of delay and jitter and may cause asymmetry. But you can have many different other ways of sharing a time base as long as it is the PTP timescale. So just be creative. This is a new problem and there may be many more solutions. Then you have the stream reliability problem, because you're on the WAN and you will have network congestions and leak failures, and losing a packet will happen. So what can I do? Well, using purely AES67 you cannot do much because none of that is precise in the standard. However, ST2110 and especially ST2110-10 recommends the use of ST2022-7 or multipath redundancy. And along with all other techniques such as forward error connection, stream reliability transport, or RIST, all those techniques are available to strengthen the connection in terms of recovering lost data. So let's see a bit more on that. First, you have FEC, which brings partial redundant data within the stream. This means that when you are using one packet, you can recover it using the ancillary data that is bring up with the stream. But unfortunately, for FSA to be performant, you need only sparse loss of packets in the stream. On the other hand, instead of sending twice the bandwidth like you would with ST2022-7, you would only send it with a coefficient of 1.1 or 1.2. Then you have restore SRT, which are request protocol, meaning that the receiver, when missing a packet, will request it back to the sender. Then the sender will send it again until the receiver receives it or gives up on asking the same packet. And there are more problems and there are more solutions, and it all depends on the techniques that you're using for the WAN, optical networks or internet or MPLS networks, and your use case, which in turn will mean expected performances. And high expected performance will do not necessarily translate to the same solutions as a low expected performance, of course. Then, the good thing is that AES67 is based on IT standards, and notably RTP, which is one of the heart of AES67, is widely used over the internet for many years. And maybe the stream that you are looking right now, maybe it is using RTP. Also, AES67 does not require any specific transport equipment. This means that by design, AES67 can travel over the internet with no limitation other than the one that are physically imposed by the size of the network. On the other hand, AES67 is also using PTP, and PTP was not designed for WAN. So your PTP performance across the WAN may vary on the scheme that you use to share the time base. And of course, on the WAN, and especially it is forbidden on the internet, you don't have any multicast, or it is very specific to use multicast on a WAN. So the go-to method here is to go to unicast. So what should I expect? Well, with care, AES67 can go over any IP network, but the link offset will often be more than 20 milliseconds. And maybe up to, for transcontinental transmission, it can go up to 1 second. You will have some clock offsets, meaning that some differences in clock synchronizations between those different sites. But depending on the techniques that you use for clock synchronization or on the performance, clock performance that you expect from your system, this might not be really problems. You will have dropped packets, but if you use redundancy, then you can cope with that. And you can have a perfectly good wide area network transmission when using the proper techniques. And you can use gateways, you can use boxes that take care of that for you. And there are companies that provide those gateways, or you can build that yourself. The key here is system design. And system design takes time, but it's rewarding because you will design your system based on your expectations and the performances that you want. Thank you.